Cool. All right. So, like I said, we're going to start in on a new chapter here. This is now moving on to chapter 10, which focuses on a new functional group, one that we've talked about before as products of our reactions. Now we're going to kind of feature them here, talk about their properties, alkyl halides. All right, so an alkyl halide is when we have a hydrocarbon chain that has some halogen bonded to one of those carbons. All right, and our halogens here are fluorine, chlorine, bromine, and iodine. All right, any one of those would be considered an alkyl halide if bonded to a hydrocarbon. Importantly, we kind of put fluorine in its own little class. Alkyl fluorides don't really have the same reactions of alkyl chlorides, bromides, and iodides. So a lot of the reactions that we're going to talk about are going to focus on the latter three here, the latter three halogens. But nonetheless, anything that has a halogen, any organic molecule with a halogen bonded to it would be considered an alkyl halide. All right, so let's start off talking about our functional group's physical properties. All right. First physical property is the polarity of these molecules here. So let's take a look at a specific alkyl halide. All right, what do we think? Polar, non-polar functional group. All right, we have this polar carbon-halogen bond here. Right, my halogens are on the more electronegative side, pulling electron density away from that carbon atom. So these are indeed polar bonds. All right. But how I want you to think of our alkyl halides is, although they are considered to be polar molecules, they are weakly polar. All right, kind of surprisingly so. And this is a little bit of a complicated picture. It has to do not only with the dipole moment in that bond, but also how polarizable those halogens are. Nonetheless, the way that I want you to think about our alkyl halides as being polar, yes, but as being weakly polar. They're very much so on the weaker side in terms of their polarity. And so what type of interactions do they have with neighboring alkyl halides here? Dispersion, dipole-dipole, or hydrogen bonding? What's the strongest one going to be? Dipole-dipole. All right, so these can dipole-dipole interact with neighboring alkyl halides. All right, so then in terms of their boiling points, we said that our alkanes are very low boiling points because they were non-polar, having very weak dispersion forces. Considering that these are weakly polar, we're even going to say they have weak dipole-dipole interactions. They also tend to have low boiling points. All right, not very low boiling points, but definitely on the lower end of our boiling point spectrum here. All right, in fact, I think it's kind of helpful to get an idea of what I mean by weakly polar is to take a comparison of a few different molecules here. We want them to be of similar size. Remember, if we're going to compare molecules in terms of their boiling point, larger molecules always have higher boiling points than small molecules. So if we want to compare functional groups, we want to do so with similarly sized molecules. And we're going to rank them from lowest boiling point to highest boiling point. All right, our alkanes indeed have very low boiling points. All right, so we're going to look at 2-methylpropane. We're going to compare that to an alkyl halide that has a similar size. So we're going to have to use our small halogen fluorine here. Comparing that to another polar molecule, one that also only has dipole-dipole interactions, acetone. And then lastly, one of our functional groups that can hydrogen bond are alcohols. All right, and we're going to put numbers on here looking at these boiling points. All right, but what I want to sort of keep in mind here is that our alkanes only have dispersion forces, whereas our alkyl halides have those dipole-dipole interactions. All right, what about acetone? What interactions would this have with its neighbors? Also dipole-dipole. And as I said, our alcohols can hydrogen bond. All right, so indeed, our alkanes here with their very weak dispersion forces have the lowest boiling points. All right, this is going to be negative 12 degrees Celsius. And our alcohols have higher boiling points. Whoops. This would be 83 degrees Celsius. 82 degrees Celsius. All right, but now we're going to compare our alkyl halides and acetone here, both of which have these dipole-dipole interactions. But again, what I'm trying to illustrate to you is just how weakly polar these alkyl halides are. All right, so our 2-fluoropropane here has a boiling point that's only negative 10 degrees Celsius. Right, so the interactions between neighboring alkyl halides here are pretty similar to that of our alkanes, compared to acetone, also only has dipole-dipole interactions, but now has a boiling point of 56 degrees Celsius, right? So again, what we want to think about with our alkyl halides is that they have these very weak dipole-dipole interactions, right? Compared to acetone, this is a nice, good, strong polar bond here. Strong dipole-dipole interactions. All right, and then now, so that was an alkyl fluoride. Let's take a look at an alkyl chloride. Same idea, but now we're just going to replace that fluorine with a chlorine. This chlorine here is much larger than that fluorine atom. It also doesn't hold on to its electrons very tightly since it's so big, so it's more polarizable. So what would we expect? Would it have a higher boiling point or a lower boiling point compared to our alkyl fluoride? Larger atom here. Higher boiling point. And still not quite as strong. Even though that chlorine atom is huge compared to that oxygen, still only around 36 degrees Celsius. So still weaker interactions than neighboring acetone molecules have with one another. All right, but we can note here in terms of our trends of our boiling points, so let's just call this trends of alkyl halides. An alkyl fluoride is going to have a lower boiling point than an alkyl chloride, lower boiling point than an alkyl bromide, lower boiling point than an alkyl iodide. All right, we can see in terms of our trends of our alkyl halides, our boiling point increases with increasing halogen size. All right, and so just we sort of think about, we already kind of have maybe a little bit of an intuitive sense of this. We know that in the lab we work with dichloromethane a lot. Dichloromethane does not mix with water at all. So even though it's technically considered a polar molecule, we think of it as pretty far on the end of that non-polar spectrum, right? Just barely polar molecule. One reason why we love alkyl halides, and what we're going to see, we use them a lot. We're going to talk about them this chapter, we're going to talk about them next chapter, is that these alkyl halides are good electrophiles. Similar to alkenes, they are great starting points in an organic synthesis. They react quite readily because they are good electrophiles. All right, and this just goes back to what we were showing before. We have this polar bond. So we have this carbon atom here that lacks that electron density, getting pulled away by my halogen. All right, so it's a good electrophile because it lacks electron density. All right, I guess specifically that carbon. But we talked a lot about electrophiles previously, and electrophiles, yes, they have to be relatively electron poor, but they also have to be able to accept a pair of electrons. So what is the other feature of an alkyl halide that makes them such good electrophiles? Specifically, what role does that halogen play? Plays the role of a leaving group, right? So that's also why these are such great electrophiles. Yes, our carbon lacks electron density, but we could make that same argument with an alcohol, and an alcohol is not a good electrophile, right? What makes alkyl halides unique is that they have these good halogen leaving groups, right? So my halogen is a good leaving group. Cool. We will sort of focus on the electrophilic nature of these functional groups in our last few chapters in this course. We're really winding down here, right? We're in the last unit. Okay. Since we introduced a new functional group, the first thing that we're going to do is talk about the nomenclature of these alkyl halides. All right, so let's get an example down here. All right, and one of the things about alkyl halides in terms of nomenclature that's a little bit unique is if I asked you what the functional group was in this molecule, you would tell me alkyl halide, right? If you said alkane, that would be wrong, okay? What's going to be weird about our nomenclature for alkyl halides is normally our functional groups are built into the back half of the name, right? So alkanes end in ane, alkenes end in ene, alkynes end in ine, alcohols end in all, right? Usually we're changing the suffix in the back half of our name. For alkyl halides, these halogens are not treated as functional groups that go in the back half of the name. They're treated as substituents. They go in the front half of the name, all right? So we're just going to make a note here that what's going to be unique is that our halogens in the world of nomenclature are substituents. So in step 1 here, where I'm finding my parent chain, my longest continuous set of carbons, so these 1, 2, 3, 4 carbons here. All right, but we don't change the ending on our parent chain name. So for an alkyl halide, we still use that ANE ending. So my parent chain here is a butane. All right, what's going to be unique here is that we treat those alkyl group, or rather those halogen groups, as substituents. Okay, so our fluorines are considered fluorosubstituents. All right, just be careful, really easy spelling mistake. A lot of people try to give me fluoro. It's F-L-U-O, not F-L-O-U. All right, so fluoro. Chloro is a chlorine. Bromo is a bromine. And iodo is an iodine. So this thing here is a bromo substituent. All right, and then we're going to number our parent chain. All right, and because in the world of nomenclature, these are substituents, we don't have any sort of prioritization like we had with our other functional groups. All right, so when we number, we simply want the lowest number in the name. And then we assemble everything together just like we always did. So when I number my parent chain here, I want that bromo group on the lowest possible number. So this would be 2-bromobutane. All right, we're going to do one more example here so I can illustrate my point. Okay, we're going to find our longest continuous set of carbons. 1, 2, 3, 4, 5, 6. So what's my parent chain? Hexane keeps that A-N-E ending. So this is a substituent, specifically a methyl substituent. This is a substituent, specifically a fluoro substituent. And I'm going to number my parent chain here, 1, 2, 3, 4, 5, 6. Or I can go the other way, 1, 2, 3, 4, 5, 6. And which one of these numbering schemes is correct? All right. Again, we do not consider this to be a functional group in the world of nomenclature. This is a substituent. So there's nothing special about it compared to my other substituents, my methyl group. I don't prioritize my halogen in any way, shape, or form like I did my other double bonds and triple bonds, stuff like that. So I'm just looking for the lowest number in the name. I'm going to make a list. Blue is a 2 and a 4. Red is a 3 and a 5. So I want my blue numbering scheme here. All right, so in terms of numbering, we want the lowest number in the name, and we're just going to remind ourselves, we do not prioritize those halogens. So this one here, when I put them together, I do still put it in alphabetical order. So this would be 4-fluoro, 2-methyl hexane. All right, so even though this molecule here is not an alkane, it ends in ANE, but it is not an alkane. If I asked you for the functional group and you said alkane, it'd be wrong, right? It is an alkyl halide. It's just in the world of nomenclature, we don't treat those halogens as back half of the name functional groups. We treat them as substituents that go in the front half of the name. Cool. All right, so now we're going to talk about our first reaction of these alkyl halides here. And this is what's called radical halogenation. Okay, so first of all, our halogens, all of our halogens, fluorine, chlorine, bromine, iodine, they are all these diatomic molecules, right? So you don't find individual chlorine atoms floating around. You always find individual chlorine atoms flying around. You always talk about chlorine molecules, Cl2, which if we're going to draw our Lewis structure for, we got these two chlorine atoms bonded together with a single bond. All right, and of course our halogens, to complete their octet, they like to have these 3 lone pairs. So 1 bond and 3 lone pairs for my halogens. Okay, one of the things to note about these halogens, let's go look over here. I can ignore this for a second. This is a table of what's called bond dissociation energies. This is how much energy you have to put in to break a particular bond. So for example, if I had hydrogen gas, H2, if I'm trying to break that hydrogen-hydrogen single bond, I'm going to have to put in 436 kilojoules for every mole of hydrogen atoms that I have, right? In order to break bonds, we have to put in energy. So this is a table here of a master list of these bond dissociation energies in organic chemistry. All right? And what I want to do is I want to focus in here on the subset that corresponds to our halogens. And I want you to look at these values carefully and compare them to all the other values that we see on this table here. All right? What do we notice? Are they big? Are they little? Yeah, so compared to every other bond dissociation value on here, our halogens have very weak bonds. All right, so we do not have to put very much energy in to break this chlorine-chlorine bond at all. All right, and this is going to really be important for the reactivity of these halogens. You might have heard that chlorine gas is something that's very toxic. Why is it so toxic? Because when you breathe it in, it instantly reacts inside your lungs to form hydrochloric acid. And guess what? You don't really want hydrochloric acid inside your lungs, right? So these halogens are all very reactive because those halogen-halogen bonds are very weak. All right, so we're just going to note we have these very weak bonds here. Okay. These bonds are so weak that they can undergo pretty easily what's called a homolytic cleavage. All right, this is a weird type of bond breaking, something that we haven't seen before. All right, it's called a homolytic because the bond breaks evenly. All right, so this is what would be called a symmetric bond breaking. Okay, and if a bond is going to break symmetrically, a bond consists of how many electrons? So if this bond is going to break symmetrically, that means 1 electron goes over here and 1 electron goes over here, right? So in a homolytic cleavage, each atom gets a single electron. All right, so we talked a little bit about these special electron pushing arrows, these fishhook arrows that we use to represent the movement of single electrons. So if I was going to show a homolytic cleavage here, I would show 1 electron jumping onto this chlorine atom and the other electron jumping onto this chlorine atom. Again, we're using these fishhook arrows. To show the movement of single electrons. So not pairs of electrons, but individual electrons. So 1 electron jumps onto 1 chlorine atom, the other electron jumps onto the other chlorine atom. All right, so if we're going to draw our product here, we have one chlorine atom has now accepted this one electron. My other chlorine atom has accepted the other electron. So in a homolytic cleavage, our product here are these atoms that carry just these single unpaired electrons. Does anybody remember what we call these? Free radicals. All right, so what we get from this homolytic cleavage is what we call a free radical. All right, so what do we know about these free radicals? What do we know about these unpaired electrons? Are they super happy being unpaired? No, they're absolutely furious, right? So these things are super reactive, these free radicals. All right, so then what is our radical halogenation reaction here? Oh, real quick before we jump on, let me just note that this bond is so easy to break. We don't have to put very much energy into it at all. We can actually accomplish this homolytic cleavage by just shining in some light on that molecule. All right, so in order to create this homolytic cleavage here, we're going to just hit our chlorine gas with some photons. All right, whenever you see H nu, it means that you're shining in light or sending in photons to your sample. Okay, cool. So then our radical halogenation here is going to take advantage of these chlorine radicals or of these halogen radicals here. And what we're going to do, our substrate here. Remember I told you that alkanes were really boring functional groups. And they only had those reactions, those combustion reactions. Well, that was kind of a lie. They are really boring functional groups. But it turns out that if you react them with these super pissed off radicals, you do indeed have a chemical reaction that occurs. All right, so if we take chlorine gas along with an alkane, we shine in some of that light, we will get an alkyl halide product. All right, as well as HCl gas. Okay, so this radical halogenation is useful in taking those super boring alkane functional groups and transforming them into something that's a great electrophile, our alkyl halides. Cool. All right, so now we're going to look at our reaction mechanism for this radical halogenation. And this is going to be a little bit more in depth than the reaction mechanisms that we've seen up until this point. Because of those radicals, we got a few different steps that have to occur in our mechanism here. All right, so the first is what's called the initiation phase. All right, our initiation phase is when we create our free radicals. And that's exactly what we were just looking at up here. That initial homolytic cleavage of those halogens in order to create our free radicals. This is our initiation phase. All right, we took this perfectly neutral, perfectly happy chlorine gas molecule, and then we hit it with that photon, and we created these two very mad free radicals. All right, so then the next thing is what those free radicals go on and do in this reaction mixture here, what we call the propagation phase. All right, so what happens when our alkane meets one of these very mad chlorine-free radicals here? All right, well, our chlorine here with its unpaired electron is very reactive. All right, it's going to form a new bond. It's going to steal this hydrogen off of our alkyl halide here, but it's only got one electron. So in order to form a covalent bond with that hydrogen, it needs to steal half of that covalent bonding pair of electrons here. This is where our electron pushing arrows, there's a few things that are different about them with our fishhook arrows. Normally we have this rule where our arrow has to start at a pair of electrons and end at an atom here. But importantly, it's not a pair of electrons that we have. It's a single electron. And I need another electron from this bond over here. So instead, our bond formation arrows with our fishhook looks like two arrows that are pointed at the same location where that new bond is going to be. Right? So this is how we would draw bond formation with our fishhook arrows. One electron from that free radical joining another electron that used to live in this covalent bond here. All right, and this will form our HCl product. All right, but there's more to the story here. Something else is going on. Okay, so first of all, how many electrons were in this covalent bond? 2. And how many did I move with this one fishhook arrow? Just 1, so I got 1 more to deal with here. That one is going to now jump onto my carbon. All right, so when I draw my product here, what should be on that carbon atom now? A free radical. All right, so now my carbon is holding that unpaired electron. All right, I'm going to note this is in our propagation. This is step 1 of our propagation. Now we got step 2 where that carbon radical is going to react. Okay. Now importantly, we said that when we shine light on this chlorine here, we get this homolytic cleavage, right? Importantly, this is only a very small fraction of chlorine molecules that will split into free radicals at any given time, right? Let's say 0.1% have actually broken into these free radicals. Most of the chlorine floating around is still diatomic chlorine molecules. So what happens in the next phase of our next step of propagation is that carbon radical finds one of those intact chlorine molecules, and we're going to get that same sort of radical reaction here where it's going to form a new bond with chlorine where it donates 1 electron and 1 electron comes from what used to be that chlorine-chlorine bond. Again, I've only shown the movement of one of those 2 covalently bonded electrons. The other one is going to jump onto that chlorine atom. So given what we've discussed about these fishhook arrows, everybody take a second and see if you can't draw me the product of this step here, following these electron pushing arrows. All right, now we have our alkyl halide product, our new carbon-chlorine bond. What's my other product going to be? I got one of those chlorines over here. What happens to the other one? It's a radical. Now it's got that unpaired electrons. All right. So what we want to note here about the difference here between these two phases, in the initiation phase, we've created our free radicals, right? So we start off with a molecule and we create a free radical. What happens in each step of our propagation phase? All right. I start off with a radical. When these radicals react with molecules, they form radicals. Right? So notice how in my propagation step, I'm not losing my free radical at all. I have a radical on both sides of my reaction. Okay? That's what makes these free radicals so dangerous, is when they go on to react with other stuff in your body, they just continue to make free radicals. It's not like the reaction stops there. Now I have yet another chlorine radical that can just loop back and start back on step one of this propagation phase. And that's going to happen over and over and over and over again. All right, that's going to happen until we get the off chance of this termination step here, termination phase. All right, in our termination phase, this is when two radicals find each other to create a molecule. Okay. So and there are a few different things that could happen in order to terminate this reaction here. It could be that two chlorine radicals find one another. And since they both have these unpaired electrons, they can donate those unpaired electrons in order to form this new chlorine molecule. All right, or maybe it's our carbon radical that finds a chlorine radical. All right, but the bottom line is two radicals will react with one another, and we don't create any new radicals here, so that has the effect of stopping that reaction. All right, so in our mechanism for our radical halogenation here, we have a few steps. We have that initiation phase where we create our free radicals for the first time. Those free radicals will go and react in the propagation step here. Our propagation step is when radicals create more radicals. All right, so our chlorine radical reacts with our alkane, creating a carbon radical. That carbon radical reacts with a chlorine molecule, creating another chlorine radical, which will then just cycle back and continue this process over and over and over again, until we get to that random chance of two radicals finding one another in solution, our termination phase, where they create not another free radical, but they create a neutral molecule. Cool. All right, so in terms of our radical halogenation, we're taking an alkane, reacting it with a halogen under those homolytic cleavage conditions to create an alkyl halide here. So that's easy enough when we're talking about methane, but what about when we get to more complicated molecules? All right, so for example, what happens when we take butane and react it with our halogens? Let's do chlorine in our homolytic cleavage environment, right? What's our product that we get on the other side? So before we can answer this, we got to talk a little bit more about these radicals and specifically about free radical stability. All right, we talked about trends in our carbocation stability and how they corresponded with degrees of substitution. We're going to actually see the exact same thing from our free radical stability. If we're going to rank these from least stable to most stable, all right, our least stable radical is one of those methyl radicals, all right, where your carbon is bonded to 3 hydrogens. A little bit more stable than that would be a primary free radical, and a little bit more stable than that, a secondary free radical. And where am I going with this? What's our most stable one going to be? Tertiary free radical. So just like carbocations, our radical stability depends on our degree of substitution. All right, but it turns out to be a little bit more complicated of a picture than that. And in order to better explain this, in order to predict our products here, we're going to have to look at what we call a reactivity series. All right, so what we're going to do is we're going to make a chart here where we have degree of substitution. We have chlorine and bromine, so these are going to be our columns here. Turns out that depending on your halogen, you get a different preference for primary, secondary, or tertiary carbons. All right, so in terms of degrees of substitution, we're going to have these 3 options, either a primary, a secondary, or a tertiary carbon. All right, and this reactivity series is relative here, meaning that our primaries are always going to get the reactivity value of 1. All right, so our secondary carbon here, if we're doing a reaction with chlorine, a secondary carbon is 3.9 times more reactive than a primary carbon. And a tertiary carbon is 5.2 times more reactive than a primary carbon. All right. With regard to bromine, bromine is quite a bit more dramatically prefers higher degrees of substitution. It turns out that a secondary carbon is 82 times more reactive than a primary carbon, and a tertiary carbon is a whopping 1,640 times more reactive than a primary carbon. All right, so again, what does this value tell you here? For example, this means that a tertiary carbon is 5.2 times more reactive than a primary carbon when reacted with a chlorine radical. All right, we'll figure out how to use these values here in a second. This is not a chart that you have to have memorized. This chart will be on your constants page for this exam. You just have to know how to use this chart. All right, so let's work on using this here. So again, what we're trying to do is figure out what our product would be for our reaction with a more complicated molecule like butane undergoing one of these radical halogenation reactions. And in fact, we can go even further than just predicting like major and minor products. What we're going to be able to do here is determine the distribution of our products of our radical halogenation products. Meaning not only can we say major or minor, we can actually say 10% this, 70% that, whatever it may be. All right, so determine the distribution of our radical halogenation products. All right, so step one, we're given a chemical equation like this. Step one, we need to determine all our unique alkyl halide products. All right, so what do I mean by that? We have these 4 carbons here. Any one of them could be halogenated. All right, so what we want to do is figure out what our potential products are for this reaction. Okay, so since I have these 4 carbons, I could put a chlorine on this one. I could instead put a chlorine on the second one. I could instead put a chlorine on the third one. All right, or I could put a chlorine on that last one. All right, so these are all these potential products that I could get from this radical halogenation reaction. But we want to be good here, and we want to determine all of our unique possible products here. Some of these molecules, I've drawn the same molecule twice, right? Not all molecules up here are unique. And I want to make sure to only determine all of our unique possible products. So I want you to take a second and narrow this list down here to just the unique possible products. Okay, and a great way, let's say that we have 2 molecules and I'm trying to figure out if they're the same molecule, then name it, right? If it's the same molecule, they'll have the same name. So how many unique products do I have here? Just 2. I have my 1-chlorobutane and my 2-chlorobutane. But this is also 2-chlorobutane, right? I would just start counting from this direction. And this is also 1-chlorobutane. I would just count from this direction. So indeed, we only have 2 unique products here. And since we're good at NMR here, we can note that our number of unique products will depend on the number of chemically distinct carbons here. Since these two carbons are in the same chemically distinct group, they'll give us the same product. Since these two carbons are in the same chemically distinct group, they will give us the same product. All right, so kind of narrowing down my colors here. Not all four of those carbons are unique. All right, these are the same, and these are the same. So that's step one. We determined our number of chemically distinct groups. Step two. All right, we're going to count the number of hydrogens that, when substituted, would produce each product. All right, in this reaction, I'm removing a hydrogen from this blue group here and replacing it with a chlorine to get my 1-chlorobutane product. I need to figure out how many hydrogens I have in each one of those groups that, when substituted, would produce that given product. All right, so let's look at our 1-chlorobutane here. How many hydrogens are there in that blue group that, if I substituted, would give me that 1-chlorobutane? How many hydrogens are over here? 3. If I took any one of those 3 hydrogens and replaced it, I would get this product here. But not only that, same thing on this end here. How many? 3. Any one of these hydrogens, if they got removed, would give me that 1-chlorobutane product, right? So for this product here, there would be 6 hydrogens that I could remove in order to get my 1-chlorobutane product. All right, what about over here? How many hydrogens would give me my 2-chlorobutane product? 4. 2 from that one red carbon, 2 from the other red carbon. So 4 hydrogens. All right, so now we have step 3 here, which is to calculate. Calculate our percent distribution. All right, now, given what we discussed about our, where am I? Oh, sorry. Calculate, step 3, calculate percent distribution. Okay, sorry. Given what we discussed about our radical stability, which one of these products would we expect to be our major product here? The 1-chlorobutane or the 2-chlorobutane? The 2-chlorobutane, because we said that secondary radicals are more stable than primary radicals, okay? But it turns out it's not that easy. There's a bit of a numbers game going on as well. These radical reactions, this first step is to remove a hydrogen from that alkane. Well, it turns out that it's more likely to remove a hydrogen if you have more hydrogens. So the number of hydrogens is also going to factor into our calculation here. So when we calculate our percent distribution, that percent is going to be equal to the number of hydrogens times the reactivity factor for that carbon. right? So we're accounting for not only the reactivity of primary versus secondary versus tertiary, but also the number of hydrogens present in that chemically distinct group. And in order to get your percent, you're going to have to divide this by the sum of number of hydrogens times reactivity factor for all of your products. And then since it's a percent, we're going to multiply by 100. All right, so for this product here, our 1-chlorobutane. I guess let's do them side by side here. I'm going to do my percent here for this one, percent distribution. This is going to be the number of hydrogens that were in that group. So our 6 hydrogens times the reactivity factor for those hydrogens. For that, I have to go back to my series here, and I have to figure out whether I'm talking about chlorine or bromine. Which one are we talking about reaction-wise? Chlorine. And in terms of my carbon here, if I'm looking at that 1-chlorobutane, would that be a primary, secondary, or tertiary carbon? It would be a primary carbon. So my reactivity factor here is that 1. Oops. If I go over here to my 2-chlorobutane, that was 4 hydrogens times that reactivity factor. What would the reactivity be for that red group? 3.9. That was a secondary carbon. All right, and then in order to get my percent, I'm going to have to divide this by the total for everybody. So my 6 times 1 plus my 4 times 3.9, all times 100. Same denominator over here. That total number, I guess I can note this is for our red group. All right, and now everybody's going to be mad at me because I made this big declaration about how there's no math in organic chemistry, and yet we have a little bit of math that we got to do here for this particular unit. All right, I believe in us though, not too bad. All right, so if we calculated our percent distribution for our 1-chlorobutane product, we would get 27.8%. And if we did the same thing for our 2-chlorobutane product, we would instead get a percent distribution equal to 72.2%. All right, so look, we're not only able to say that this is our major product here, we can actually put a percent distribution on this here, right, using these calculations. So when we're talking about a distribution of our radical halogenation, I'm talking about what are my products. And then not only that, let me make some room. Not only what are my products, but also what is this percent distribution? 27.8% of that 1-chlorobutane, 72.2% of that 2-chlorobutane, right? That's what we mean by the distribution of our radical halogenation products. Cool. All right, I want you to do one on your own now. We're going to take that 2-methylpropane. We're going to hit it with chlorine under those homolytic cleavage conditions. And you're going to give me not only what our potential products are, but also what the distribution of those products are. All right, so we got these two chemically distinct groups of carbons. This just froze, so let me restart it. Since we have two chemically distinct groups of carbons, that means that we have two potential products. All right, how many hydrogens are there in that red group? Yeah, we got 3, 6, 9, 3, 6, 9. Right, to be clear, I'm calculating on my reactant here, because these are the hydrogens that would get substituted to create my product here. So we have 9 hydrogens on this carbon. What about on my blue carbon? Just 1 hydrogen. So now when I do my calculation here, I'm going to take those number of hydrogens, and I'm going to multiply it by that reactivity factor. Since that red group is a primary carbon, its reactivity factor is just 1. Since that blue group is a tertiary carbon, its reactivity factor is 5.2. Then I have to divide by the total, so divide by 9.1, or rather 9 times 1, plus 1 times 5.2, times 100. Same denominator over here. All right, so when we do our math, we would see that 63.4% of our product will be that 1-chloro-2-methylpropane, and the other, what is that, 36.6% is that 2-chloro-2-methylpropane. So what's our major product here? The primary. But wait, I thought that primaries were less stable than secondaries were less stable than tertiaries. So why do I have a major product here that's that primary carbon? Because there's so many more hydrogens, right? Both of those factor into your calculation. Your reactivity factor, but also just the numbers game of what hydrogen could possibly get hit. I will just note, and you can trust me on the math on this one, if we played the exact same game with bromine, come on, use that exact same substrate, but instead used bromine under those homolytic cleavage conditions, giving us our 2 alkyl bromide products. Since bromines reactivity factors are so much larger than that for chlorines, we would get 99.5% would be that tertiary product, and only 0.5% would be that primary product. Okay? Bromine, we say, is more selective. It very much so more favors the more substituted carbon compared to chlorine. All right? And the reason why that is a little bit complicated, but it actually has to do with what the other product is in that step, that first propagation step, that hydrohalic acid. It turns out that hydrochloric acid, when this bond forms here, there's a big release of energy. So it can kind of compensate for a less stable radical being formed. Whereas hydrobromic acid, when that bond forms, it actually absorbs energy. So all of a sudden, the stability of that other product matters quite a bit more. That's just fun fact. Don't worry about it. Bottom line, make sure you know how to use this table. Cool. All right, we're going to start in, and we'll pick this up next time here with our next reaction in this chapter. Again, focusing on preparing alkyl halides. This is what's called allylic bromination. All right. So first of all, just to pick this apart real quick, that first word allylic we've heard before, that corresponds to carbon-carbon double bonds, are alkenes, but a specific position about these carbon-carbon double bonds, not the ones directly about that double bond. These are what are called the vinylic positions. Our allylic positions are one removed from that carbon-carbon double bond. I guess even if this was a larger molecule here. These are our allylic positions. All right, and in allylic bromination, what we're going to do is we're going to take an alkene and we're going to brominate that allylic position, All right, so what we're going to see is these reactions here, they don't mess with that carbon-carbon double bond at all. All we're going to do is add a bromine to that allylic position, right, to that allylic carbon. So this is an allylic bromination reaction. We're going to brominate the allylic carbon. All right, this uses a fancy reagent to do it, what's called NBS. No BS here. All right? No, so NBS stands for N-bromosuccinimide. Oops. We don't really have to have this memorized or anything like that, but just a fun fact, we actually see structures that look like this quite often. So just to kind of get some eyes on this thing here, this is this nitrogen that's in this 5-membered ring, but it's flanked on either side by these 2 carbonyl groups. And then attached to that nitrogen is our bromine. Okay, let's be good. Actually, my nitrogen has a lone pair here. Similar to what we saw for our halogens, we're sort of talking about this in the same chapter here. This bond right here is just very weak. Those carbonyl oxygens are like pulling electron density away. This bond can break very easily in, again, that homolytic cleavage. Okay, so we're not going to look at our full mechanism. You can look it up. It is pretty well established here. But suffices to say that it is another free radical type mechanism where we brominate specifically that allylic position in our alkenes. Okay, notice that unlike every other reaction of alkenes where we were doing an addition to that carbon-carbon double bond, we actually don't touch that carbon-carbon double bond at all in this reaction, right? We start with an alkene, we end with an alkene. We've just got a halogen attached in that allylic position. So then why the allylic position? All right, if we go back to our bond dissociation energies here, we can look up a sp3 carbon-hydrogen bond. We can look up an sp2 carbon-hydrogen bond. Those are all over 400, 440, 460 kilojoules per mole. And then if we look at that allylic carbon-hydrogen bond, what do we notice? Quite a bit weaker. All right, so that's why that allylic position is singled out over all the other positions in those molecules. Turns out that those hydrogens are held more weakly in those allylic positions than they are in any other position on that molecule, right? Whether it's about the double bond or one of those sp3 hybridized carbons, that allylic position is particularly weak. And we'll see why that is next class period. It has to do with resonance, right? So just like we had allylic carbocations that were stabilized through resonance, we're going to see these allylic radicals are stabilized through resonance as well. We'll pick up with that next time.